Welcome to the Deep Dive. Today we're tackling a really interesting piece of work for all you AI researchers and ML engineers listening in. It's the technical report on Kimi-VL.
That's right.
So in a nutshell, this paper introduces a new open source vision language model, and it really stands out.
It does.
It's built with an efficient mixture of experts architecture MoE, right? Activating only, 2.8 billion parameters out of 16 billion?
Yeah, 2.8 active out of 16 billion total with the Moonlight language model backbone. Pretty efficient.
And it uses a native resolution vision encoder, MoE VT.
MoE VT, yeah. And delivers really strong performance across, a whole range of multimodal tasks.
Even with incredibly long inputs, right? Up to 128,000 tokens.
Exactly. That long context capability is a big deal.
The potential here seems huge, maybe closing the gap between open source VLMs and what we've seen in language-only models, especially for scalability and reasoning.
Yeah, I think that's the core goal. So today, we're really going to unpack the architectural innovations, the training methods, and the results from this Kimi-VL report.
Let's dive in. So maybe start with the challenge. Why was a model like Kimi-VL needed?
Well, it's clear that open source VLM development has kind of lagged behind pure language models in some key areas.
Like scalability.
Exactly. Scalability, especially using things like MoE, but also efficiency and, importantly, that advanced reasoning, like long chain of thought.
We've seen language models like DeepSeek R1 pushing MoE and long cup.
Right. But then you look at recent open source VLMs, maybe Qwen 2.5 VL or Gemma 3. They're mostly dense architectures, aren't they?
Yeah, and not really focusing on that super long context reasoning.
Precisely. It felt like VLMs were sort of stuck, not quite catching up on that scalability and deep reasoning front.
And there were earlier attempts at MoE VLMs, right? Like DeepSeek VL2.
There were. DeepSeek VL2 was interesting, but it had limitations. I think it was capped at a 4K context.
Yeah, 4K, which feels pretty short now.
It does. And then there was Aria, another MoE VLM, but maybe not as strong on the fine-grained visual tasks. And again, no real push into that long thinking aspect.
So Kimi-VL is aiming to hit all those points: efficiency, performance, and long context.
That's the idea. The report really emphasizes structural innovation, getting stable capabilities, and specifically enabling that enhanced reasoning through, as they call it, long thinking.
Giving the research community a more powerful, versatile, open source tool.
Exactly. Bridging that gap we talked about.
Okay, all right, let's get into the architecture then. You mentioned the Moonlight MoE language model and the MoE VT vision encoder. How do they work together?
So the core is that Moonlight MoE language model, and the key, like you said, is the efficiency, only activating 2.8 billion parameters out of 16 billion total for any input.
Which means less compute, making it more accessible.
Definitely. And then there's their custom vision encoder MoE VT. It's about 400 million parameters, and crucially, it's designed for native resolution image processing.
Native resolution?
Mm-hmm.
How does MoE VT actually pull that off? It sounds tricky.
Well, what's clever is they use a packing method, kind of inspired by Navet. Instead of forcing patches into a fixed grid, they divide the image into patches. Okay.
Flatten those patches into sequences, and then just concatenate them sequentially, like in a one long 1D sequence.
Oh, so it treats the visual input more like words in a sentence.
You got it. And that's the really neat part. Because it's sequential, MoE VT can use a lot of the same computational tools and optimization tricks that work so well for language models.
Like flash attention.
Exactly. Flash attention is key for handling long sequences efficiently. Because MoE VT treats images this way, they can use flash attention without hurting training speed, even when dealing with batches of images that have different resolutions.
That's a smart integration. But how does it keep track of where things are in the image, the spatial information?
Good question. So MoE VT starts with pre-trained weights from Cyclopeso 400M, which uses fixed-size position embeddings.
Right.
But to handle varying resolutions better, especially high ones, they added 2D rotary positional embeddings, ROPE.
ROPE, okay.
Yeah.
Across height and width. Yep. Across both dimensions. These work together with the original interpolated fixed embeddings to give a much more precise sense of where things are, especially fine details.
Which is critical for high-res images or tasks needing spatial awareness.
Absolutely. And they mentioned this 2D ROPE integrates really smoothly with their whole flattening and packing approach.
Okay, so MoE VT processes the image.
Yep.
How does that visual information then connect to the Moonlight language model?
That's the job of the MLP projector. It's basically a multi-layer perceptron that takes the features from MoonVT and maps them into the same embedding space as the language model uses for words.
Aligning the visual and text worlds.
Precisely. That alignment is essential for the model to learn the connections between what it sees and the text it processes during the later training stages.
Makes sense. Okay, let's switch gears to the training itself. The report mentions an enhanced Mewon optimizer. What's special there?
Yes, Mewon. So they took the original Mewon optimizer and improved it. They added weight decay, to help prevent overfitting.
Standard practice, but important.
Right. And they also carefully tuned the update scale for each parameter individually. Plus, their distributed setup uses 0-1 optimization.
0-1. For memory efficiency.
Exactly. It drastically cuts down the memory needed on each GPU and reduces the communication needed between GPUs during distributed training. Super important for a model this size. They used this enhanced Mewon setup for everything: VIT, projector, language model.
Got it. A powerful, efficient optimizer.
Yeah.
Now, the pre-training strategy sounded like multiple stages.
Definitely multi-stage.
Yeah.
Table 1 in the report lays it out. First was VIT training, a huge Coca-like stage, 2 trillion tokens.
Wow, 2 trillion. What was the focus there?
Mainly image-text contrastive learning, matching images and text and image captioning, learning to describe images.
Yeah.
And interestingly, they noted that even then, the model started showing some early OCR, optical character recognition abilities just naturally emerged.
That's pretty cool. So after that huge visual pre-training.
Then came joint pre-training. First, a relatively small alignment phase, 0.1 trillion tokens, just tuning MoonVT and the projector to mesh better with the language model.
Getting them speaking the same language, so to speak.
Kind of, yeah. Then a much bigger phase, 1.4 trillion tokens. This used a mix pure text data, but also lots of multimodal stuff.
What kind of multimodal data?
Captions, interleaved text and images, OCR data, knowledge-based info, video, even data from simulated agent interactions. And crucially, they gradually increased the proportion of multimodal data during this stage.
Easing the model into the complexity.
Seems like it, yeah. Helping it learn those cross-modal connections effectively. After that, there was a joint cooldown phase.
Cooldown. What's that for?
Think of it like letting things settle. It was 0.6 trillion tokens just to stabilize the capabilities learned in the intense prior stages, make sure everything was robust.
Okay, stabilization. And then the big one, activating that long context. How'd they manage 128K tokens?
Right. The joint long context activation stage, they did it in 2 substages, quadrupling the context length each time, from 8K up to 128K.
Did they have to change anything else?
Yeah, they reset the ρP inverse frequency to better handle those super long sequences. And the data mix was interesting. Only 25% was actual long context data.
Only 25%. What was the rest?
The other 75% was just replaying shorter data from the previous joint pre-training stage.
Huh. Why do that?
It seems this strategy helped the model learn the long context mechanics without forgetting how to handle shorter inputs effectively.
Best of both worlds.
Exactly. And the results back it up. Table 2 shows the needle in a haystack tests NIAH on text and video up to 128K.
And it worked.
Yeah, it could find the needle, the specific info, even in a 128K token video haystack. That's a really impressive retrieval.
That's good for video. Yeah, that's a big step.
Yeah.
Okay, so pre-training gets a solid base model. What about fine-tuning it for actual use?
Right. The post-training stages were key for making Kimi-VL more instruction following and better at reasoning. Figure 5 shows this. First was joint supervised fine-tuning, SFT.
Fine-tuning the whole model.
Yep. Language model, projector, VIT, everything. Using instruction data formatted in ChatML style.
To make it follow instructions and chat better.
Exactly. They used a mix of pure text and vision language, SFT data, and they did some smart things like masking the prompts, only training on the answers, using format-aware packing to use the context window efficiently, and mixing in dialogue data from their Moonlight language model. They actually did 2 rounds of SFT, one at 32K context, then up to 128K.
Okay, that covers general instruction following. But what about boosting that specific long thinking ability?
That was the next stage, long co-supervised fine-tuning, coate for chain of thought. Here, they use specially curated text and multimodal data designed to promote long reasoning chains. Data involving planning, evaluation, reflection, exploring possibilities.
Really pushing the complex reasoning over long context.
That was the goal, yeah. Explicitly activating and strengthening that ability.
And finally, reinforcement learning, RL.
Yep. RL to further polish the accuracy and quality. They used an online policy mirror descent algorithm similar to what they did for their Kimi K1.5 model.
How does that work, roughly?
You train a separate reward model to judge the quality of the main model's answers. Then you use that feedback to improve the main model.
Refining it based on quality scores?
Pretty much. They did online RL just on the answers, used length penalties to avoid rambling, and controlled the difficulty of the training examples.
It sounds like an incredibly thorough and carefully planned training pipeline. You mentioned the importance of high-quality data earlier. Can you expand on how they built that data set? It sounds massive.
It really does. Sections 3.1 and 3.2 go into detail. They put a huge emphasis on high-quality multimodal data, developed pipelines for filtering, synthesis where needed, and serious deduplication.
Quality control was key.
Absolutely. They broke down the pre-training data into 6 main types.
Okay, let's run through them.
First, caption data. Basic image text pairs. Use diverse open source and in-house sets, Chinese and English. Importantly, they limited synthetic data strictly.
Good. Second.
Interleaving data. Text mixed naturally with images and videos in sequence. Forces understanding of context across modalities.
Right.
OCR data. This was a big focus. Data from everywhere. Open source, in-house, multilingual, dense documents, web pages, even handwriting.
Wow.
They handled figures, tables, diagrams, scene text, used lots of augmentation, and notably, multi-page OCR data for long document understanding.
That focus on OCR definitely seems to pay off later in the results. What else?
Fourth, knowledge data, a big repository of human knowledge. They mention curated geometry data as an example for visual reasoning. Standardized taxonomy, processed textbooks, papers using layout parsers and OCR, even handled infographics.
Comprehensive. Number 5.
Agent data. This is cool. Designed to teach grounding and planning for interacting with desktops, mobiles, web UIs.
How'd they get that data?
Bulk VM management, heuristic collection of screenshots and actions, dense grounding formats, categorizing actions, icon data, even human annotated QWERTY trajectories for complex desktop tasks.
Very cutting edge. And the last category.
Sixth was just text data. They use their existing high-quality Moonlight corpus, English, Chinese, code, math, knowledge, rigorously filtered, quality controlled. They even figured out the best sampling strategy empirically.
An immense, diverse, and carefully curated data set. Okay, shifting back to training logistics.
Yeah.
How did they make training such a big model so efficient? You mentioned the speed up.
Yeah, that efficiency came from their 4D parallelism strategy. It's pretty sophisticated.
4D, what are the dimensions?
Data parallelism, splitting data across devices. Expert parallelism, vital for MoE, splitting the experts. Pipeline parallelism, splitting model layers across devices. And context parallelism, helping manage those long sequences.
Combining all 4.
Right. By optimizing workload distribution across these 4 dimensions, they got about 60% higher training throughput compared to a similar size, say 7B parameter, dense VLM like a Qwen 2.5 7B based one.
60% faster. That's a massive saving in time and cost.
It really is a significant practical advantage.
So all this hard work, architecture, data, training, it must have led to some strong results. Let's talk evaluations. What stood out in the report?
The results in Section 4 and Appendix B are definitely impressive. They show Kimi-VL performing really well across a wide range of tough benchmarks. Table 3 has a big comparison against models like GPT-4o and other open source ones.
Okay, let's break it down. How did it do on, say, those hard college-level academic problems?
On benchmarks like MMMUVL and Video MMU, which test academic knowledge, Kimi-VL actually outperformed DeepSeek VL2 and was comparable to Qwen 2.5 VL.
Which is pretty good, considering Kimi-VL uses fewer active parameters.
Exactly. It speaks volumes about the efficiency and the architecture's effectiveness.
What about just general multimodal understanding? Things like MMBench.
Across a whole suite, MMBench EN, MMStar, MMVet, Real-World QA, AI2D, Kimi-VL was very competitive, often beating other open source VLMs. Its MMBench score was right up there with GPT-4o Mini, actually.
That's notable for an open source model. What about reasoning across multiple images? That's getting more important.
Yeah, on the B-Link benchmark for multi-image cognition, Kimi-VL showed strong results, again beating several open source competitors in reasoning about info from multiple pictures.
Okay, moving to tougher reasoning. Like math. How did it handle Math Vista or Math Vision?
Pretty well. Competitive performance, sometimes even leading the open source pack. It shows a good ability to mix visual input with mathematical steps. Figure 8 in the report has a nice geometry problem walkthrough.
Cool. Now that OCR focus you mentioned earlier, How did it perform on text recognition and document tasks?
This was definitely a standout. On InfoVQA and OCR Bench, the results were exceptional. It surpassed GPT-4 Mini and DeepSeek VL2.
Really? Better than GPT-4 Mini on OCR?
According to the reported scores, yes, highly proficient at pulling text from images accurately. Figure 9 shows the range complex tables, math formulas, even handwriting. It handles them surprisingly well.
That level of OCR in a general VLM is huge for applications.
Yeah.
Okay, what about agent tasks? Interacting with UIs?
Another strong area. On single-step grounding like ScreenSpot V2 and the harder ScreenSpot Pro, it was accurate at finding elements on screen.
And multi-step tasks?
Even more impressive there. On things like Osworld and Windows Agent Arena, where it has to perform a sequence of actions, Kimi-VL often outperformed GPT-4o and other top models. Figure 10 shows it navigating Chrome to turn on Do Not Track, a clear example of multi-step GUI interaction.
Wow, that's getting close to genuinely useful agents. And video, with that long context, it should shine, Rob.
And it does. Across benchmarks like Video, MMU, MMVU, Video, MME, and especially Long Video Bench, it showed strong performance. General understanding, long video summarization, Q&A on long videos. Figures 11 and 12 highlight this. The long context really pays off for video.
It really sounds like a versatile powerhouse, but no model is perfect. What limitations did the researchers acknowledge?
They did point out a few things in Section 5. First, model size. While efficient for really specialized problems or ones needing super deep language skills, the current size might still be a bit limited.
Makes sense. What else?
Reasoning capability. It's strong, but they feel it's not at its theoretical limit yet, especially for highly complex multi-step inference tasks.
Room to grow.
Yeah. And finally, the long context. Even at 128K, they note the attention layer parameter count is like a 3B models, so for truly massive sequences, it might still hit limits.
Okay, reasonable limitations. What's their plan for future work then?
Pretty clear roadmap. They want to scale up the model size, expand the pre-training data further, more diversity, more quality, refine the post-training algorithms for even better reasoning and instruction following.
Bigger and better versions?
Seems so. They mention releasing larger versions and also refining post-training and test time scaling to build even better thinking models.
It definitely sounds like Kimi-VL is a major contribution to the open source VLM world. That mix of MoE efficiency, the Mewon VT native resolution handling, the strong performance, and the long context, it really does fill a gap.
Absolutely. Its potential impact, especially for research and applications needing that long context multimodal understanding or agent interactions, it's huge.
And being open source is key.
Totally. It democratizes access to this kind of tech and just opens up so many possibilities for researchers everywhere.
So for all you AI researchers and ML engineers tuning in, here's something to think about. Now that we have an open VLM like Kimi-VL, with this specific set of capabilities, what new applications, what new research avenues does this unlock? Especially in those areas needing long context understanding or complex visual interaction.
It's an exciting question.
Definitely dive into the Kimi-VL technical report for all the nitty-gritty details. Thanks for joining us on this deep dive.